Hi! Welcome to another lecture video of Math 21. In this video, we'll talk about local linear approximation, differentials, and marginals. We all know that one of the easiest functions to evaluate is a linear function. It's a function of the form g of x equals mx plus b, where m and b are just constants. In this video, our goal is, given a function y equals f of x, we want to estimate the value of f of x and delta y, it's just change of y, using a linear function. This special linear function is called the local linear approximation. So, for this video, we will only talk about the first half. So, this will be the first part of two videos. And we will focus on differentials and local linear approximation for this video. For the next video, we will have approximating delta y and marginals. So, let's start with differentials. So, given a function y equals f of x, here, with this graph, the curvy one, and consider the tangent line to the graph of f at the point P. So this line here. Okay. So if you remember, the point P is the point of tangency, and it has the coordinates x0, f of x0 in our diagram, and okay. So, do you remember how to compute or what is the slope of the tangent line to the graph of f at P? Okay, so it is simply the derivative of f evaluated at x0. That's correct. So, it's just f prime of x0, the slope of the tangent line to the graph of f at P. So now, our question is, do you remember the limit definition of this one, the derivative, f prime of x0? So, so it's actually this one, okay? It's the limit of, so do you remember how this was derived? So, this expression here stands for the slope of the secant line passing through P and Q, okay, where Q has coordinates x, f of x. Okay, so why is this slope? Because it's the numerator is the difference of the y coordinates, while the denominator is the difference of the x coordinates. Okay, so it's the slope of the secant line joining P and Q. So what you do is you get the limit of the slopes of the secant lines as x becomes closer and closer to x0. So as this point Q travels along the graph of f and getting closer and closer to P. Okay, so if you take the limit, then you will get the slope of the tangent line. So this expression, we will try to rewrite that this way. Okay, so for the numerator, we write it as delta y. So this will just stand for the change in y coordinates. So f of x minus f of x0. And delta x is the change in x coordinates, so x minus x0. So we have here the derivative f prime of x0 equal to this expression here. Alright? So, what can we say about this equation? This means that if delta x is small enough, and maybe I need to talk about delta x approaches 0. So as x becomes closer and closer to x0, we know that delta x is the difference between x and x0, right? So as x becomes closer and closer to x0, what happens to your delta x? Your delta x becomes smaller and smaller as well, and it approaches 0. And that's why you can replace x approaches x0 with delta x approaches 0. Alright? So back to our thing here. So in other words, what does this mean? If delta x becomes small enough, then the quotient of delta y divided by delta x is approximately equal to f prime of x naught. So that's what this means, right? And delta x, we can multiply that both sides so that we will have this expression. And how do we read this? This reads as delta y is approximated by f prime of x naught times delta x. Okay? And this expression on the right is actually called a differential. Okay? In fact, this is the differential of y. And this is our definition. So the differential of y with the symbol dy is defined as the derivative of f multiplied by dx, where dx is the differential of x and it just denotes an arbitrary increment of x. What does that mean? It just means that dx is just a change in x. And that means dx is nothing more than delta x. So these are just the same. Okay? Next, if dx is not 0, then from this expression, we can divide both sides by dx and we get this. Does it look familiar? Yes, because this symbol, dy over dx, we always see that when we get derivatives, right? Because this is actually a symbol for the derivative of y with respect to x, or the derivative of f with respect to x. But this time, because of the notion of differentials, we have a second meaning for this symbol. That is, this can also mean as the quotient of the differential of y divided by the differential of x. Okay? So now we have two meanings for this symbol, the derivative of y with respect to x and the quotient of the differentials of y and x. Okay? So let's try some simple examples in finding the differential dy given these functions. So it's very simple. All you need to do is to find the derivative. So here, find the derivative and multiply by dx, and you're done. Okay? If you're still having a hard time, it's not hard. All you need to do is get the derivative dy over dx and then just multiply both sides by dx, and that's it. Then you get dy. Okay? So for the second, it's also easy. Just make sure to apply your chain rule first. So derivative of the outer function is 1 over 2 square root of, copy the inner function, and then multiply by derivative of inner function, and then multiply by dx. That's it. So differentials will be used to define our local linear approximation. So do you remember our diagram from before? So we will just add this particular detail that dx is just delta x, but it's still x minus x naught, and delta y is our difference of the y coordinates f of x minus f of x naught. And then recall from a while ago that if delta x is small enough, so this difference is small enough, then your delta y, or your change in y, so that's this one, right? The change in y is that, okay, is approximated by this expression here, okay? So we're going to make this a bit nice. So we will replace delta x with dx, and as well as here. And also, what does it mean if delta x is small enough? It means that delta x is close to 0. And replacing that with dx, then we can say that if dx is close to 0, then delta y is approximately this one, but replace delta x with dx. Okay? Then let's make it nicer, a bit more. So we replace delta y with this difference, f of x minus f of x naught. Okay. And yeah, by the way, this expression on the right is just familiar, right? It's actually your dy, right? Okay. So again, we will replace delta y with f of x minus f of x naught. Then copy the right-hand side. Then we transpose this to the right side. And then write dx as x minus x naught. And therefore, we will get this expression. So f of x is approximated by the expression in blue. Is this expression familiar? So do you remember how to get the equation of the tangent line to the graph of f at a certain point, say x naught f of x naught? So how do you get the equation of a line? All you need is the point-slope form. Okay, so you just need a point on the line, which is this one, x naught f of x naught, and the slope of the line. So in this case, what is the slope of the tangent line? It is f prime of x naught. So plugging them in, you get this equation, and then transpose f of x naught to the right, you should get this. Oh, so this blue expression comes up again. It's exactly that one. Okay, so these are exactly the same. So what does this mean? This tells us that the blue expression is just the y values of the tangent line. Okay, so from here, what does that mean? Then this means the values of f of x are approximated by the y values of the tangent line. Okay, so in other words, if dx is close to 0, if it's small enough, or in other words, if your x is close to x naught, okay, then f of x is approximated by the tangent line to the graph of f at x naught. Okay, and this tangent line has a special name, and that's exactly your local linear approximation. But let's look at this illustration. So when x is close to x naught, it says f of x is approximated by the tangent line. In this case, the tangent line is blue and our f of x is black. Okay, so we can see that as x becomes close to x naught, the blue, okay, and the black dot, okay, so the y values here are very close to each other, right? And they become even closer as x becomes closer and closer to x naught. So that means that the y values of the tangent line, the blue dots, they approximate the y values of the graph of f, which is the black dots, when x is near the abscissa of the point of tangency, which is this point. And again, this line is called the local linear approximation of f at x naught. So how do we write it? We write it in this way. So L of x equals this expression on the right that we saw earlier. Okay, so if you're asked to find the local linear approximation of f at x naught, then you only need two things. It's your function f and your particular value of x, which is x naught. Okay, so maybe a few comments on the name. Why is it called approximation? Because it approximates your f of x. Why is it called linear? Because it's a linear function. As we can see here, it's just point-slope form, right? Or mx. You can write it as mx plus b. Okay, and then finally, why is it called local? Because the approximation is only good if your x is close enough to x naught. Okay, so that's why it's local. So this local linear approximation is considered as the best linear approximation of f near x naught. And you remember this expression we had before? We can actually rewrite this in another way. So how do we do it? So remember that dx is delta x and delta x is x minus x naught. So we can transpose x naught to the left side. Then we will have x equals x naught plus dx. So we replace x with x naught plus dx, and we replace x minus x naught with dx. So this entire thing here will just be written as this one. Okay, so x naught plus dx, and then this one is dx. Okay, so this alternate form is actually quite useful. So we will be using it in some examples later. So let's have our first example. Find the local linear approximation of this function f at x naught equals 8 and use this to estimate this constant, right? So how do we start? Again, let's write the formula for the local linear approximation. So it's this function, linear function. So all we need are what? The function f and x0, both are given, so plug it in. First, we have to get your derivative of f, very simple. And then plug in your 8 in your function and in the derivative, so you should get the following. So L of x is, so this is f of 8, f prime 8, and x minus 8. Okay, and then what is f of 8? It's 2, then this is 1 over 12, then this is just copy, and this is your local linear approximation, and you can box that. But there's a continuation. You have to use L of x, or the local linear approximation, to estimate this constant. So how do we do that? We first write the constant that we want to estimate, and then we have to write this as f of some number, okay? But our f is cube root of x, so what should the number be? The number must obviously be 8.03. So this constant is just f of 8.03. And then do you remember our local linear approximation? We know that f of x can be approximated by the local linear approximation L of x. So this is approximately equal to L of 8.03. So if this is x, then that's x. If it's 8.03, then this is also 8.03. And then use the formula that we already have here to, and we will have 2 plus 1 over 12, and then plug in 8.03 for your x, and you have this. So here, this is just 0.03 divided by 12. So what is our final answer? Should it be in fractions or in decimals? It's better to write it in decimals because we want to have a numerical estimate. Okay, so 0.03 divided by 12. To make it easy, what you can do is to write 0.03 as 3 times 0.01. So 3 over 12 is 1/4, and that's 0.25. And then multiply that by 0.01, then you get 0.0025. Okay, so plus 2, then the answer is 2.0025. Alright, so this is our numerical estimate for cube root of 8.03. So if you use a calculator, what is cube root of 8.03? It's actually, okay, the actual value is this one. Okay, so notice that it's quite close. It's good enough as an estimate. Okay, so this is how we use the local linear approximation to estimate certain constants so that we can have numerical estimates. Okay, so let's try square root of 15.96. So in that case, again, if you notice, it's quite different from the first example, because for the first example, the function f and x0 are already given, but in this case, it's not. So maybe for this example, let's try to use the alternate form, the red one. So, but for this alternate form, we actually need 3 things. We need to choose your f, we need x0 and dx. So these are the things that you have to choose by yourself, okay? Because it's not given. So your function f is a bit obvious because a while ago we had cube root of x, right? But now it's, instead of cube root, you have square root. So maybe it's a good idea to write f of x as square root of x. By the way, it's also easy to get f prime, so just write it down. And then let's decide what x0 and dx are. So how do we do that? We want to write your constant here, 15.96, as the sum of x0 plus dx. So that if you plug that in to your f, you will get f of x0 plus dx, right? Yeah, so that's what we want. So we just need to figure out what x naught and dx are. So usually we choose x naught to be an integer, okay? And that integer should be close to your given constant. Okay, why do we want it to be close? So that your dx will be small enough, meaning it's close to 0. Okay, so what is the closest integer to 15.96? It is 16. Okay, so if this is 16, then obviously your dx must be negative 0.04. If you're not, if it's not that obvious, then what you can do is, if you write here 16, you can transpose to the left, then 15.96 minus 16 is just negative 0.04. Okay, so using these two, then we are ready to use the formula. Okay, so first write your constant, the given constant that you want to estimate, and then write that as f of x naught plus dx. So is it true? So x naught plus dx is indeed what? 15.96, right? 16 minus 0.04 is 15.96. And if you plug that into your square root of x, then you get exactly this. So this is true. So this constant is f of x naught plus dx, where x naught and dx are 16 and negative 0.04 respectively. And now, we are now ready to move on to the second part of the formula. So this is approximately equal to, so copy. So x naught is 16, and dx is negative 0.04. So you should get this. Okay? And then plug in all your 16s to your function and f prime. Then you should have 1/8 multiplied by that. And again, if you're having a hard time, what we can do here is write 0.04 as 4 over 8 times 0.01. So that's 1/2 or 0.5 times 0.01, which is 0.005. Okay? So, right? Okay. And then subtract this and you should get 3.995. And this is now our numerical estimate for square root of 15.96. So let's take a look at what you will see in the calculator. The actual value is this one. So, good. Good estimate. Okay, and for the last example, let's try a more challenging one. So notice that there are two constants involved, 0.01 and 0.98. So if you have more than one constant involved in your expression, what we can do is choose one of them, okay, to write as x naught plus dx. So in our case, let's choose 0.01 because it looks a bit easier than 0.98. In that case, if your x naught plus dx is 0.01, what is your x naught and dx? So x naught we can choose to be 0, okay, because it's the integer closest to that number. And therefore, dx will be positive 0.01, okay? So using this x naught and this dx, we have to find out what f of x is, okay? So obviously, since x naught plus dx is 0.01, this cosine 0.01 we'll just use what f of x. This is just cosine x, okay? But for the other one here, what will be your function for ln 0.98? So remember, 0.98 is close to 1, but what is it? It's 1 minus 0.02, right? So just try to relate that with what you have here with your x naught plus dx, which is 0.01. So how do you relate 0.02 with 0.01? So 0.02 is just 2 times 0.01. Then therefore, you can write the function for ln 0.98 as ln 1 minus 2x. Okay? So, why is this correct? Because if you plug in x0 plus dx to f of x, so if you plug in 0.01 to f of x, then you will get cosine 0.01, and that's correct. And here you will have 0.01 times 2 is 0.02, 1 minus 0.02 is 0.98. So you get exactly the same thing. Okay? Alright. So using this function, then we will apply our local linear approximation. So for that, we try to get your derivative first as usual. So what is the derivative of this? So just be careful, you have to use product rule. Yes, so derivative of first, make sure you use chain rule and then copy the second, and then copy the first, and then derivative of the second. And you get this. So let's proceed with the actual estimation. So copy what you want to estimate and then write it as f of x0 plus dx. So in that case, it's f of 0.01 or x0 plus dx. So f of 0 plus 0.01. And now follow your formula. This will be approximately f of 0, f prime 0, and 0.01. And then solve for these values. F of 0 is simply cosine 0, 1, ln 1, 0, so 0. F prime 0 is sine 0, 0, ln 1, 0. Cosine 0 is 1, this is 0, so this is negative 2. Times 0.01, and it's negative 0.02. And that is your answer. What is the actual value? It is this one. So, kind of close. Okay? And that ends the first half of our topic. Stay tuned for the second half. In that video, we will talk about approximating delta y and marginals. So, see you in the next video. Bye!